Thanks everybody for joining me for the second lecture of the series. So, are there any? I think I've addressed all the. I tried to address all the concerns from the first lecture. Well, let me know in chat, or otherwise, if there are more. All right, let me. Look at my notes. So, so today we're going to talk about how quantum groups going to appear in the picture, but before, and I need my glasses. Before that, I think I'd like to take 5 minutes and explain a few things from the end of the previous lecture, just to make it maybe make a connection with something you might have seen before, so that make it a little bit more concrete for you. So I recall what were the kind of problem we were talking about. We had a Riemann surface, some genus G with some marked points. And we were studying maps of this Riemann surface, map of some degree f equals t, to some variety x, which for the purposes of let's try to draw a more. So this is for the purposes you can start with x. We discussed it in if you try to define a quantum field theory, your local space of states x could be some pretty general set. But when you compute the index, you might as well assume that this is already some component. Well, maybe not the whole thing, a component of the modulo of vacuum. Meaning that if you vacuum describe states that exist without change in infinite space and infinite time, and you think if your surface is very, very big, which you can certainly assume computing the index, then a low energy state would be a modulated vacuum, and this map F describes the vacuum modulation, like how the actual vacuum changes from a point to point in this Riemann surface. So okay, this may be all a little abstract, so you can but so this is, I recall that this was supposed to be space. This surface C was the space, was the physical space, and we're computing an index in some 2+1 dimensional quantum field theory, and so the index corresponds to the time direction. But I think everywhere in physics, you would agree that once you understand this theory in flat Euclidean space, you already understand. Then putting it in general manifold, this seems like a kind of a much easier. So once you understand the theory on flat Euclidean space, then you almost understand you understand the essential part of it. So what would be that? So let's just talk about that. So if you have so now of course our curve C, let our curve C be, so sorry, C, the curve C will be C. So maybe R2 if you think of flat Euclidean space, and we would like to and we would like to understand the situation with that. And what is it? And well, of course, this is non-compact, and so then we would to assume that so as usual when you put a theory in an infinite space, you have to assume that at infinity it is in one particular vacuum. So this is we have still maps to X, but the boundary, so the infinity, maybe I'll highlight this infinity. So highlight this whole thing is going to, so maybe, so this was my X, so X looks, one knows what that X looks like. Let's just draw a picture, something like that. So this is my X. And then this whole thing is mapped to one particular point in X. So this is saying I want to study situation in a flat Euclidean space, and with boundary condition that at infinity I'm in one particular vacuum. So the way to say it in algebraic geometry is that, well, of course you have that is you have a map of the Riemann sphere. So this would be P1, and then there is this point at infinity. And what I would like to say that this map F, so I have my map F here, so that map F of infinity is some given point in X. And moreover, that I'd like to this is not all. This is I'd like this everything near infinity things look regular. Means I'd like this map to be non-singular. It means F prime of infinity that is not zero. This is not so to speak, it's not equal to non-singular, finite. Right, so this is not only it takes this value, it takes this value in a differentiable way. So this is, so if you, this is an analog, if you might have, well, I'm going to talk about more complicated things, but you might have seen the more complicated things before. And if you, in four-dimensional gauge theory, this is called like a Nekrasov precision function, where you study a four-dimensional gauge theory with, and you compactify it on S4, and you assume that at this infinity of S4, nothing happens. Or another object is given J function. So this is object of the same kind. So this object is really so this is, instead of looking like some infinite dimensional space, this in fact looks like an open set. So this is an open set. Open set in this space of maps. And our goal, I remind you what we were trying to integrate over all maps from our Riemann surfaces. We'd like to compute some kind of, not integrate in K-series. So on this moduli space, we have some local index, and we would like to push forward that index. Well, this means in an integral and push forward in K-series means you have some imagined vector bundle, and push forward means you take its sections, but maybe not only sections, but also whole hierarchy homology. And so this means if I take push forward from an open set, well, what does it mean? Push forward means it takes sections. Of a holomorphic vector bundle. An open set. So this is in general would be infinite dimensional. So this general. So this is infinite dimensional vector space. But from the very beginning, we weren't interested just in vector spaces. We were interested in in group actions on these vector spaces. So we have some automorphism group of, so here on X, we have the automorphism group of X. And here, well, maybe preserving, you want to, maybe you want to fix that point. So maybe you want to fixing that point that we want to say that infinity. So this is okay. And then similarly here we have an action of the automorphisms of P1 fixing that infinity. And most importantly, here we have just rotation by Q. And so this means that this infinite vector space, so the character, so we have some group acting on an infinite dimensional logical space, but the character is well defined. Character of our group action of the automorphisms of P1 fixing infinity cross automorphisms of X fixing that marked point. This is well defined. This is well defined. And in fact is a rational function. Function for given degree D, which is the degree of this map. And then if we want to sum over all degrees, so then we want to sum over all degrees. So we sum over all D. We remember, we introduced a new variable to remember the degree of that. So maybe take the D. And so this was so we think of this. This is well, everywhere in mathematical physics, everywhere in this course, we'll be using generating functions. And in fact, we'll use generating functions today in a more essential way. But here, this is the way you should think of this is a placeholder for remembering the degree, but also you can think of this as since we would like everything to look like a covariant K-theory, we would like to say that this is like a character of the torus, for which, so we'd like the degree of the curve to be a character of our torus. So the torus will take this second homology of X, Z coefficients, and take sensor product. Well, I'll write C star, which is multiplicative group of your field. So and so this is times this rational function times this rational function. And so this rational function, this is a function of some variables. We would like, so there was this variable Q, remember, and then we need some kind of coordinates on this space. Remember that we had, well, so let's denote summarily this, well, there's some coordinates here. And very generally, this rational function, this is in fact will be this expression. So in fact, this is going to be some fancy, well, maybe not so fancy, maybe a fancy generalization of the Q hypergeometric function. So what is a Q hypergeometric function? This is a function of the form, maybe I'll write it C. In classical situation, it depends on three variables, A, B, and C. You should think of this as kind of the coordinates on the group, and the variable Z and the variable Q, so maybe like that. So these are the this A, B, and C are the coordinates that are right here. And so this is summation over D. You take Z to the D, and the coefficient of Z to the D is a product of some kind of Q factorial expression. So you write it A, D, B, D over Q, D, C, D, where X, D, this is 1 minus X, 1 minus QX, and so on, 1 minus Q to the D minus 1X. And once you get comfortable with the equivalent K theory, it'll be obvious to you that this sort of expression is just a particular K-theoretic, bare natural K-theoretic expression in this context. You can also write it as a difference, as a ratio between X sort of infinity. I mean, you imagine an infinite product of this kind and divided by Q to the dx infinity. That's one way to write it. And what unites all these functions? These are solutions. Solutions of regular Q-difference equations. So there was a question. This A, B, and C. Well, I'm writing general kind of the simplest example of the kind of function you're going to get. And A, B, and C are the functions, are the variables which go by dots here. So Q-difference equation in the variable Z, but also so this is something one has to show. It's not obvious at all. Like for example, if you write an across a function, it's not a solution of any equation or any simple Q-difference equation. And also in variables, not in all variables, it satisfies Q-difference equation in all variables, maybe, and also a difference equation. A Q-difference equation. In the automorphisms of X variables, which is regular in the variables that preserve the symplectic form. So that's a subgroup here. And so what would be the kind of the duality that we discussed at the end of this lecture? So duality from X to X check, this exchanges. These are so in compact geometry, I said the actual indices have to be equal, but in a non-compact geometry they're not equal, and it's very easy. But they exchange their solution of the same difference equation. So this is exchanges these variables and these variables. So this says for two dual geometries, the coincidence of indices is true not only for compact geometry, but in fact true for pieces. So the most fundamental piece is just the flat space, and in the flat space, it's not the same function. Then we have to understand. Well, it has to be kind of important to understand how these two functions are different, but they solve the same Q-difference equation. So That is, and so example, where you might have seen this before. So example, if I take Macdonald polynomial, so this is P, maybe call it P lambda of X, depends on some variable Q and T. So this is a terminating case. Like typically in a hypergeometric function, there is some possibility for the series to terminate. Like you look here, there's if one of this, if this A or B, if one of these factors becomes 0 at for some D, then it'll be stay 0 for all D, for all subsequent D, and so the series will be just really a polynomial. So a Macdonald polynomial is a terminating case of a certain hypergeometric function. Where you have to specify maybe variables. So this has some variables called A1 through AN, and you have to specify. So lambda was a partition, so you have to specify it like Q to the lambda 1, T to the N minus 1, this sort of thing. Q to the lambda rho, so to speak, Q to the lambda N. Then the series terminates, and you get for this. And no, this I'm talking the GLN Macdonald polynomials right now. So Macdonald polynomials for the group GLN. And so then the kind of remarkable fact is that this there's a label argument symmetry of Macdonald polynomials. This says that the equation, yeah, well, here's X is a vector. And this is a partition. Lambda is a partition. Thanks, Anton. So X is a vector, X1 through Xn. So there's a very nice label argument symmetry for Macdonald polynomials, and it says that these equations, so it satisfies the equations in A, well, are upon, you have to identify things correctly, but they're the same as the equations in X. And in particular, when you have a terminating case, then this means you have particular rational function solution of the Q-difference equation, which is very special. And so if the equations are the same, that means the actual solutions are the same. So this is when you have a Macdonald polynomial that has this kind of symmetry between its label and its argument. And so this is an example. This is an example of the general theorem for X being the cotangent bundle of GLN mod its Borel, and it's in this case it's equal to sub 2. So in GLN Macdonald polynomial, the difference equations come from Chernykh algebra, and the Chernykh algebra has a symmetry. It takes a root system, but in fact it takes kind of roots and coroots. And if you want to exchange the variables and the labels, then you have to go to Langland's dual Chudnik algebra. Well, Chudnik algebra is the same, but polynomials, the way you construct the polynomials, you have to choose one side, and so you have to choose either roots or co-roots, and then this disable. So that's the kind of. So this is the kind of thing that we would like to understand, but maybe more understand generally. But maybe I'll explain in this case that this is in this particular instance that these Q difference equations, there are many ways you can think. Well, some Macdonald polynomials are ubiquitous, and there are many ways you can think about difference equation for them. But the Q difference equations for GLN Macdonald polynomials are a special case of so-called dynamical equations. Equations for the dynamical equations of Okounkov and Enumerative. Well, many people wrote about dynamical equation. I don't mean to belittle the contribution of everybody else, but let's just name maybe the best paper to read about this called Quantum Wild Group and Applications. So that is a paper by Okounkov and Enumerative. For they studied for quantum groups associated to Kac-Moody the algebra. And we would like and to write our difference equations that we will need slightly more general theory. So we'll so we'll need more general theory. We'll need to generalize that. So the way, and the okay. So this brings us to the actual topic of the lecture, namely introduction to quantum groups. And what I would like to say from the very beginning is that I would like to present the subject in a way which does not start with generators and relations. And this is not a productive way to think about what we're going to write down, for the simple reason that the quantum groups that we will need are in principle infinitely generated. And even so, if you just look at the generators for how you write generators for quantum loop groups, then it's this is if you're an outsider, it's difficult to get into the subject. And but in general, if you're writing explicit generators and relations for the algebras you want to study, this is akin to writing. So if you have an algebraic variety, you'd like to write maybe its explicit coordinates in the equations. Well, if you think about this moduli spaces that we just discussed, like the modular space of map from Riemann surface to some variety X, if you think about you can try to think what would be like to write down the equations for that space, and that would be really complicated. And not only is it complicated, it will be rather pointless, because not only you'll spend a lot of paper writing it down, and not clear how you're going to use it. So we would like, in representation theory, we would like to act as operate as algebraic geometers operate, namely we don't write equations. We just kind of talk about equations. So this is there's some set of generators. One can be. So anyway, I don't want to make a long monologue. Maybe better if I. So this is. But I would like to say that I'd like to present a subject from a very geometric point of view, because, like I said, if in principle the groups we will need, they have infinitely many generators, and it's hard to enumerate the generators, and it's even harder to write down relation between them. While if you think about it geometrically, that becomes much easier. So maybe I'll start with what is a quantum group. And this is a quantum group is an algebra of a certain kind, and so maybe to motivate the discussion, let's start with an example. Let's start maybe let me choose a different color. Say let G be a finite group. So then to the finite group, we can associate an algebra, which is just a group algebra. So KG. So this is a field. You can also study it over. Later we will need to work over some rings. So maybe maybe rings sometimes. So this is elements here are just formal linear combinations of elements in the group. So this is some summation CGG, where this lies each of these lies in K, and you add and multiply as you would. And so in some sense, this captures, in a way, this captures the entire representation theory of this group G over that field K. So and very often, most of the time, well, it depends on your point of view. Like if you want to take with complex coefficients, then this would be just direct sum over all irreps of G, and you take the whole algebra of endomorphisms of that irreps. So irreps V, irreps M, called the module of G, had the whole M. And so, in some sense, it tells you exactly what the irreducible representation are. On the other hand, of course, it forgets a lot of information. Like many different groups will have the same group algebra. So if I'd like to reconstruct the group from the group algebra, then I have to remember that so this are maybe, okay, this are. So what makes a group different from just an algebra is that the group GX G. So the category is that the category of G modules has two structures that a general algebra would not have, and when has first of all, it has tensor product. So when you have one module and another module, you can form their tensor product. And that tensor product has a unit. This is maybe trivial one-dimensional representation. And in another object, it has duals. So you have kind of M dual, the space of Holmes from M to K. This is also so the group group as opposed to a general algebra, the group knows how to act in the tensor product and knows how to act in a dual space. So this is how does it act? Here it acts by, so an element G, if I have an element G here it acts by G tensor G, and here it acts by G inverse transpose. So if you pass the dual, of course you need to you take transpose of all operators, but to be at a representation, then you need to invert. And so this means you have two structural maps in addition to what you had before. You have a map which is called co-multiplication, so I denoted delta. So this is a map from, so this is, let's take delta G. This is a homomorphism of algebras. So you have the group algebra goes to its tensor square. And this is and the analog of this with then the unit means, so this is the analog of the fact that the tensor product is defined for any number of factors and respective of the order. Then this means this is this thing is co-associative. And unit means, so and the unit with respect to the tensor product, unit means that you have a map. So trivial representation. One means you have a map. Means you have a map from your algebra to just the field itself, and it plays the role dual to the unit. This is called co-unit. You had an algebra. We had an algebra with unit, and unit means a map from the field to your algebra. But this plays the opposite role. And then this means inverse is an antipode. This object here. This is called antipode. Means a map S that goes from your algebra. We have element G goes to G inverse your algebra here, which is, so this needs to be algebra anti-automorphism. When we act on the dual space, we take transpose anyway. Taking a transpose is puts the operators in the opposite order from which they started, and so to make it a representation, we have to make it an anti-automorphism. So this is anti-automorphism. And they have satisfy all sorts of relations, satisfy natural relations. Such as, for example, if you want to write the fact that if I take such as, you want to say G times G inverse equals G inverse times G, well, you equals one in the group, then this means graphically. So there's a convenient graphical calculus, and I have to recommend you the book by Schiffman and Vassero, which I think a marvelous book about quantum groups. So this is there's a convenient graphical calculus that says that if I I represent the coproduct by kind of a fork that goes from 1 to 2. So maybe this stands for a coproduct. The coproduct takes one argument and outputs 2, and then I can put antipode in either, and then I need to. And so then here I take the product, so maybe called multiplication. So if I take this kind of diagram, so this corresponds to the fact that I took my algebra, I took an algebra to algebra square, so this is got 2 elements here. I'm not sure what that sound was. I got 2 elements here, then I inverted one of them, I applied antipode in one of them, and then I multiplied them together. So algebra always comes with a structural map from 2 copies from 10 to the square of the algebra to itself, so that's somehow good. So that map is equal to, you do it the opposite way. There's a coproduct, there's my antipode, there's multiplication, this sort of thing. And what does this mean? This means I compose. First, I forget what. So this is, well, maybe I'll say compose unit. Let's co-unit. So this. Okay, so that's the relation, and you can either try as an exercise, write down a complete set of relations, or look at it and go. I mean, in many books on quantum groups, but the one I particularly like is the one by Okounkov Enumerative. This is the way it explains this part. So these are the axioms. These are axioms for a Hopf algebra. And the remarkable fact about Hopf algebra is that the axioms are all mirror symmetric. If you take the set of axioms and you look at them in the mirror, you read them backwards, then they read exactly the same. So this is, you can see this axiom. So this axiom, you read it backwards, then it is exactly the same axiom. So axioms are kind of a remarkable fact. And so this was with a finite group. Now, if you have a Lie group, if G is a Lie group, right? Sorry, I forgot to say. So this is the set of axioms are forgive me. So the set of axioms is self-dual. Set of axioms are, so there's a duality. Duality is reverses or errors. And then for every Hopf algebra, there's a dual Hopf algebra. And so then if I take the dual Hopf algebra for the group algebra here, would be functions on my group. So these are functions on G. And so this means, well, the operations are product. Multiplication is just multiplication of functions. And if I want a coproduct, so if I take a coproduct of a function, this now becomes a function of 2 variables. So if I want to evaluate it on a pair of elements, well, what choice do I have? I just evaluated it on the product. And this is, you can check as an exercise. This is exactly the dual. So if G is a Lie group, I have many options. So if G is a Lie group, there are many options for KG or the dual. So one is we can just take, again, say the same thing. Just form finite combinations on group elements that's somehow perfectly well defined as before. Or you can think of a finite combination of your group elements as a collection of delta masses at the group. So you can say instead you take just kind of, you know. So if you think a collection of delta masses, then you can replace it by general measure. So signed measure. So it means signed means it's not. So measure, we usually, when you talk about measure, usually we think of this something positive. So if you forget that condition, then you can take signed measures on G, and the operation so this is the kind of the multiplication is as before. So that's so if you, what do you mean to multiply two signed measures? Means you put it on two copies of the group and you push it forward on multiplication map. So that's just generalized multiplication here. Or measures are just the way the measures are defined. They're dual to some function space. And so instead of if you do different function space, and you will be talking about distributions on G. And in particular, you can talk about distribution supported at the identity. So inside here, what are the distribution supported at identity? That is the same as the universal enveloping of the Lie algebra of G. So this is, as an algebra, this is something, you know what it is, but it's as a co-algebra, means that the co-product of some element xi, that is xi tensor 1 plus 1 tensor xi, which is just the Leibniz rule. So we know the G goes to G tensor G, and if you think G is 1 plus something in infinitesimal, then by Leibniz rule we get this rule. But also you can apply many different other functors. It needs to be you apply some functor which has some multiplicative and covariant structure with the group elements. So you can put like the cohomology of the group G with arbitrary coefficients. So this is the operation being that if you have now how do you multiply two homology classes? Sorry, you put them on the product and you push it forward under multiplication. So that's multiplication. And then here in the dual side, well, we can take just functions in whatever category. So this would be the same. If you're doing Lie groups, you can take functions in whatever category. Right, so this is, you can, if you had an algebraic group, you can take algebraic functions. If you had a Lie group, you take a smooth function, you can continuous function, whatever. So this is but then the analog of homology, that is cohomology with arbitrary coefficients in a ring. So maybe A has to be a ring, so it needs to multiply. So and this is the case. This is the original case. Investigated by Hope. So Hope's proved that if I have a compact Lie group, then its cohomology is a free skew commutative algebra on some finitely many generators of 4 degrees. So that's the way he proved it is he observed that this object is Hopf algebra, and then he proved a general statement about finite dimensional Hopf algebras. So it's a beautiful argument. So now a quantum group is the deformation of any of this in the world. Of Hopf algebra. And the main direction in which this deformation, so that's definition if you want to say. So the main direction in which this this deformation is going is that if we look at this column here, so this column here, like for example here, you see that this is, while the multiplication in the universal developing algebra is commutative, this is not commutative. The co-multiplication here is commutative. So it means you take, or you have a group, everything comes from the co-multiplication for the group itself. The delta applied to G tensor G, which is symmetric. And so all of these guys are well, there's some sign rules in homology, so ignoring that these are co-commutative. And similar in this column, we look at the dual things. So then what was co-multiplication here becomes multiplication for this object. And again, ignoring the fact that they're odd cohomology classes, they don't commute the anti-commute, or these are commutative. So these are commutative but not co-commutative, and these are co-commutative but not commutative. And this is and the deformation is that to give up on that. So we'll be looking at this complex in this part, and then we want to say that we would like to give up the fact that this is co-commutative. Means if I have my product, and this is an important piece of my product here, co-product. This is in general not equal to if I take the co-product and I permute the factors. That's the deformation that we want. So this is the if I take the co-product and permute the factor, that's a different co-product. So this has the name. This is called opposite. So this is the deformation when we looked at what we would like to achieve is that co-product is no longer co-commutative, and that's but not too non-commutative. So this is I remind you that in universal developing of Lie algebra, we have a relation. That if I want to multiply x and y and compare it with multiplication of y and x, this is I don't know how to say it categorically, or this is you take the multiplication of x, y, and then compared with multiplication, you precompose with the permutation of x, y. This is like the so multiplication is the delta co-product, and if you permutation goes on the other side, and this is like, so maybe I'll remove the argument. This is you want to compare multiplication minus the multiplication with permutation. So that's the commutation relation here. So this is not some arbitrary element. This is, well, in fact, a commutator of x and y. So so this is in my Lie algebra G. So this is some object that is already given to me. It's not I go go crazy and just make this two things be absolutely unrelated. Similarly here, this delta and delta opposite will be related. So this is like saying in Lie algebra I have a commutation relation, which says that This tells me how to commute two elements. Here will be a co-commutation relation. Will be by a co-commutation. And rather than developing a very, very general theory, then we need some particular class of examples. And I don't want to do some very, very general theory. Instead, I would like to explain what's going on, and then just specialize to some particular class of constructions, some particular class of examples that we will need. And concretely, we want a deformation. So we had the universal enveloping of some Lie algebra G hat, which I'll explain what this thing is, and then this would want to be deformed to some quantum version, where what G hat is would be a loop algebra. So G hat, it will be a Lie algebra of maps from some group G. So G would be, so this G could be, so maybe I'll put it in a different color. This could be the additive group. The multiplicative group. Or maybe an elliptic curve, or this is later. It's not for now, because elliptic curve doesn't have so many global functions, so one has to, but one has to, and so this would be going to some Lie algebra G, and commutation multiplication formula. Commutation taken pointwise. In other words, if you want to introduce a coordinate on this additive group or multiplicative group, this is, you take like the G and you join the polynomials in some one variable T, which is the coordinate on the additive group, or you take G and join an invertible element. So this is for G additive or G multiplicative. And so that this is, so you have either polynomials or Laurent polynomials with values in G, and then you can, of course, you can commute them pointwise or coefficient by coefficient. This is, you understand how this is done. And the category of modules, the category of modules that we want to study is of the following kind. So first you take, so deforms is deforms, study deforms. Deforms modules of the following kind. You have my Lie algebra G, this is maps. Well, first thing you can just evaluate at a point. At some point AI, go to your Lie algebra G, and so this G itself would be some infinite dimensional Lie algebra, but okay, well, we'll worry about it later. But so this, you shouldn't think of G as an infinite dimensional Lie algebra, but you think of this maybe something representation theory which we understand better. So here for G we can take maybe we go to maybe it acts in a Maybe we have some like highest weight modules for this. So maybe I put the highest weight module. You can discuss, since J is an main principle be infinite dimensional Lie algebra, you can discuss what sort of module you're going to stick in here. But let's say, I'll say highest weight module M. And so you first evaluate AI, at some point maybe A. And so then this is this combined module we denote. So combined denote M of A. Makes sense. And so then the category we want to study are just finite tensor products of Mi taken at the point at I. So, and it's clear that different points. So you have some polynomial, and you allow to yourself to evaluate the polynomial at different points. It's clear that different points just don't talk to each other at all. It's a different points. Points AI don't talk to each other. In other words, if you have if you allow yourself a polynomial, it can take any given value at any finite set of points. So you can take, so your algebra, if you evaluate at finitely many points, your algebra projects to so many copies of your algebra G. So that's and so in particular, this is reducible. It would be reducible if HMI is reducible. And AI is not equal to AJ. This is not a very interesting category, and so in particular, any map between such things will have to be either zero or invertible. And so, right, so this is so. So in particular, if I take two such, now upon deformation, if I take M1 of A1 tensor to M2 of A2, and if I compare it with the same thing taken in the opposite coproduct, well, first of all, these are two irreducible modules, since if A1 and A2 are generic, then these are two reducible modules, and you'd think that what could have happened to these two reducible modules? They're probably isomorphic, and so this means so this is not ridiculous if you have a so this is. And so this means there is, so what will happen for us is that there is an operator called the R matrix. So there exists an operator R matrix, depends on these two modules. And two variables A1 and A2. is an isomorphism for A1 and A2 generic. Well, generic means previously the two modules. So this is if it's a non-trivial map, it has to be an isomorphism. The modules are reducible, and previously they were irreducible as long as A1 was not equal to A2. If they're actually at the same point, then they have a chance to become reducible. And now that point where they become reducible, that point might have moved. So it may have, this map may have a kernel and co-kernel at some particular values of A1, A2, but otherwise it's isomorphism. So what does it? This means that that this is in fact this is a rational matrix. So generic means some isomorphism between away from finitely many points, and this is a rational functional matrix. So it's a rational function of Na2 with non-zero determinant. And in fact, so this our algebra before the deformation, our algebra had an obvious automorphism. Namely, there was an action of the group itself. So if I have the group itself G was acting on this, because it acts on the domain. It acts on the domain of the map, and so by precomposing with an automorphism, it acts on the algebra. This is called loop rotation. And so this is if we would like to preserve the automorphism, if the loop rotation in our deformation, the loop rotation survives, and so it only depends, and so this only depends. So this matrix only depends on the ratio. We'll denote it by the variable u. So this is so maybe to explain where we're going, I'm explaining that there is a certain, for this deformation that we have in mind, there's a certain structure, and I'm not proving now that the structure exists. I'm going to take the opposite road. Is I will first construct that structure, and then the rest, this will be, and then the rest of the quantum group comes from that R matrix. So we will be, our strategy would be to first. So our strategy first construct this. The rest, including the Lie algebra itself, would follow. So I started with, I gave you some unspecified Lie algebra, and said, okay, we're going to deform the universal developing, and this will have this extra structure, this co-commutation relation that says how the two tensor products are different, two tensor products taken into different orders, how they're different. But in reality, what we will take is the opposite road. We will first start with this co-commutation relation that's given by some matrix, which we'll construct geometrically. So this will be done. This will be done geometrically. So this will be some. I'll give you some operator, geometrically defined operator. They'll satisfy some relations, which we'll discuss in a second. And then from that knowledge of that operator, one can reconstruct the quantum group and in fact the non-quantum group to the Lie algebra itself from which we start. And so what are the relations? What are the relations? So this, maybe I'll say R will satisfy the following relation. So first is that the first relation is called unitarity. So first, if I have two modules, I'll just write them. Let me drop the argument. So if I'm looking for the intertwiner between this and this, then the way to have this intertwiner is to first apply the R matrix and then permute the factors. And because the way that there will be an intertwiner, this object is called R check. And then of course you can apply this R check again. And so then what you're going to have is a non-trivial. If you take the square, you're going to have an interesting map from this module to itself. And so you might have seen pictures in ordinary kind of textbook or quantum groups. You might have seen pictures like this. So this is like a braiding. It's like applying kind of R check once, and then you braid again. So this is it's like I have a ribbon and you twist it. And typically this is non-trivial, but in our case, this in fact will be 1. So this is the identity. But this is, what does it say? That says that if I take the unit relation called unitarity, or whatever, you could call different things, but that says, what does it say? That says that what does R check square equals 1 means concretely that if I have the R matrix kind of acting in 1, 2 variables of some variable u, and I compose it with the 2, 1 variables of the variable u inverse, that is that entity. That's the related one. And this kind of pictures, this sort of pictures, this appears usually in works on R matrices without spectral parameter. This parameter u called spectral. So this is the so when you talk about like knot invariance and things like this, and you work with constant R matrices, not R matrices that are dependent on a spectral parameter, and they're obtained from R kind of R matrix. They're obtained by plugging that parameters be equal to 0 or equal to infinity, this things like this. And so then this is well, I'm implicitly here. I'm using the notation as if I was working with a multiplicative group. But so So because it's the multiplicative group gives you kind of not invariant type of things. And so then, of course, if you specialize U to be 0 infinity, then of course the relation that R checks squares, since this relation inverts U, it's lost if you specialize U to be 0 or infinity. So that's this is, you think this is less general, but in fact it's more general. This relation, which looks not like a braid relation, but it's like symmetric group relation, is in fact more general than this relation. It's like saying that well, we'll get there. And also similarly, if you want to reorder, if we want to put so this is one relation, and the other relation, if I want to have triple product, then there are two different ways to put it in the exact opposite order. So two ways, and you'd like to compare. So if you have two different operators that go from here to here, then well, you can ask, what's the relation between them? And the relation, so this relation between them is, in principle, could be something, but what will happen in our case just equal two different ways to order to put in the opposite order. Are simply equal. So this is the famous Yang-Baxter equation. So this is the well, this is the equation that I have behind me. So this you can see this is this is the Coxeter relation for S3, or the braid relation, or if you have three things you put them in opposite order. You can, there are two ways to do it, and in fact they will be exactly equal. So this is the right. So this is right. Anton is right, and I'm going to write it out. The Yang-Baxter equation with spectral parameters read. So this means the way. So the way to do it is well, that's actually notation that precedes the theory of quantum groups, because quantum groups originated from this study of vertex models in 2D statistical physics. In a vertex model, you had kind of, you think of an R matrix. You think of an R matrix as an interaction. There's some degrees of freedom that live in some module. Maybe call it M1, in some module M2, and they each have its own variable called rapidity, or somehow whatever M2, and then here, when they interact, that means here you have this R matrix R12 of A1 over A2. Okay, so this is in 2D statistical mechanics, this was actual vertex interaction. There are some degrees of freedom that live on these four edges, and the weight of their interaction is given by a matrix that goes something is given by four indices, but you interpret four indices as a map from one tensor product to itself. So that's how you interpret. That's how you interpret matrix with four indices. And then Yang-Baxter equation, the equation that's behind me, says that if I have this kind of crossing, what is this? M1 of A1, M2 of A2, M3 of 3, that this crossing, so this is a product of 3 R matrices. This is the same as this crossing. Just really the same. Just really. And so this means this is 2 operators. This is something with 6. This is something with 6 indices, and you interpret as an operation from one triple tensor product to another triple tensor product, and these 2 things are just really equal. And you can think of this as from the point of view of 2D statistical mechanics. You think of this as a invariance of your model with respect to some local rearrangement, which is like a combinatorial analog of. So typically, if you study quantum field theory, then it's very valuable that to know that it's covariant with respect to local changes of coordinates. Like, for example, it could be conformal. That's super powerful. And then in combinatorial situation, you can ask for how it responds to combinatorial changes coordinates, combinatorial rearrangement. And here it says that's actually equal. So that's actually equal. And so this is a data. So this is the data. This R matrix is the data would be constructed geometrically. But I'm only on page. I have, let's see, I have 9 pages of notes for today's lecture, and I'm on page page 5. Well, I'm not gonna get where I was planning to get, but let's postpone the geometric construction of this operator, and let's just I want to say that there's a certain reconstruction theorem that says that if you have this R matrix that satisfy the Young-Baxter equation, the unitarity relation is less important. If it satisfies the Young-Baxter relation, then in fact your modules are modules over a certain quantum group. So and so what we would like to say. So then one kind of remarkable fact. From R matrices, one gets. So R matrices are solutions of Young-Baxter equation, and makes this tensor products of this Mi or M whatever Ki of AI modules. Or a certain quantum group. And so that the R matrices are exactly the co-commutation relations. So that they're exactly there. And well, I would like to, this will probably mean going a little bit over time, but I would like to explain this because I think, well, maybe I'll start and then next time we continue, because I think it's kind of very important philosophical point. And so maybe I'll write some, so a very good, somehow 2 references I like are, one is a very old one. One is a paper by Reshetykhin, and that precedes, this paper precedes the famous Reshetykhin, Faddeev, Taijan paper. It's called quasi-triangular. Well, I think it's precedes, I don't know, it's also Reshetykhin. Quasi-triangular Hopf algebras. and invariance of length. And this is published in Algebra and Analysis, so it's really like this, Algebra E Analysis. This is how it's listed in MathSciNet. It's volume 1. So this very first volume of this thing, it's 1989. And there's also, of course, also Okounkov, and some also books by Etienne. I said there's a really good book by Okounkov and Schiffman, and there's another book by Okounkov and collaborators on quantum group on tensor categories. But how do we get this? So we have a solution. So what's the data? The data, we have a solution of this Yang-Baxter equation for some collection of spaces. And the data is first we extend. Sorry. So steps. Steps first, we extend. Extend is kind of R, M1, A1, M2, or maybe R, M1, M2 of the ratio A1, A2. To now we have two modules of this kind. So we would like to have tensor product. And the way to do it is you, I'll write it pictorially. So we have one tensor product in some particular order of this MKI of AI. And then you have another tensor product some also in some particular order of this MLI of BI. Then what I'd like to do, I just imagine this being correspond to a bunch of these lines as before. So previously 1R matrix was corresponding to one line. And then if I have a bunch, then I have a bunch of them. So this is starting from A1, A2, B1, B2. And I just multiply all R matrices in the order given to me. And this will be a product. This is a product of, in this case, 3 times 4R matrices. And it satisfies Yang-Baxter. And the way it satisfies Yang-Baxter, I mean, the way I usually explain it's like this: when you think of a picture like this, then you think, well, maybe these are 3 pieces of rope that represent this. So each one of them is a piece of rope, and then what we're doing is we put somehow move the middle string to go from one picture to another. But if you think, what is a piece of rope? A piece of rope is a whole bunch of threads. And so when you move that rope, you move a million threads. And so that is exactly what's happening in this picture. If you want to move, 2 such composite R matrices, you just move each thread. So that's the explanation. Second, and then define extend to duals. And this is done explicitly in Reshetikhin. There's a unique way you have inverses and transposes. We're not so interested. I forgot to say if you have a Hopf algebra, if the antipode exists, it's unique. It's like saying if I have a group, if it's actually a group, then the inverse is unique. And so the same in the Hopf algebra. So there's a antipode is not really a new structure. It's just a statement about non-degeneracy. If it existed before the deformation, it exists after the deformation. No, but now let's not focus on this too much. And then now we define operators. And the why we define the operators is that here we have, so here we'd like to say, so here we had this some space which was like a product of this Li's of Bi's taken in some particular order. And again, we think of this like that. So we'd like to define an operator in this space. Well, we take an auxiliary space, which may be of the kind, I mean, it's of the kind that we discussed, but let's not worry about that auxiliary space. And so that auxiliary space gives some R matrix, which in fact, if you look at closely, could be really a product of a whole bunch of R matrices. So but you should think of this as just one R matrix, crossing all of that. And then we take matrix coefficients. So this goes to auxiliary space. Take matrix coefficients here. So this would give you, or better to say, so, you know, I said we were very fond of generating functions. And so if you just take this matrix, this will be a matrix full of matrix of rational function of some whole bunch of variables. And so you treat this one object as a generating function for, first of all, you can take each, so this big matrix compounds a lot of matrix entries in it. So this is like a generating function in terms of it's one object that remembers many matrix entries. But also it depends on some variables in some, so that in that sense it's also a generating function in that sense. So this means it really gives you an operator valued in functions, and you can in principle take coefficients or any such thing, but it's better to just keep it as a. We were trying to construct a representation of like a loop group, and you got a loop group, you got something valued, like an operator valued in functions of auxiliary variable. That's super. This is what we wanted to construct, and so that is how you construct this guy. And so then, these are the operators. And so then the next time we will start with verification. You can so point is that this really so this matrix element is really this matrix element is really generating big generating function of operators. Because this auxiliary space may also be infinite dimensional, and then so this is some big object. But each I mean, if you could decompose that big object into individual pieces, for each individual piece, you're gonna get some operator that acts in your physical space. These are the operators of your quantum group, and this is if you want a product and co-product, that is clear. So the product, well, we'll start next time with discussion. If you want a product of these two things, well, this is the product. This is a picture of product. If you want a co-product, then here's a picture of co-product. So next time we'll start with detail, with a little bit more details of this contraction. But what I was trying to say is that if you have this solution of Yang-Baxter equation, that already is That already does give you a quantum group of the kind you want, and you can analyze it further, see what's in that group. But it's that's basically what it is. So all right, this is not what I wanted, what I wanted to say today, but it's how much I have time, and in fact, I'm running over time. So questions? Oh, so this is what I said, is that if you take the axioms of Hopf algebra and you reflect them in the mirror, just look at them in the mirror, then the product becomes coproduct, coproduct becomes product, and the axiom, all the set of axioms go to themselves. And so in particular, for any Hopf algebra, there's a dual Hopf algebra. Well, in fact, many depends if you're aware of infinite dimensional space. There are many notions of what it means to be dual of infinite dimensional space. But there's a notion for Hopf algebra is a dual, and the operations of the dual Hopf algebra are the mirror reflection of the operations of your original Hopf algebra. No. This is not about 3D mirror symmetry at all. So this is just about, this is like so this is really, it's no, it's all I'm saying is that if I look at the, something like this, and if I look at it in the mirror,
I wanted to write no. Yes, sorry.
It looks like that. So what was the? So that's all I'm trying to say. So this, if I have a 3D mirror symmetry, much more complicated subject. This is just saying that for every Hopf algebra, if I pass to the dual spaces and I have a choice of what what sort of dual spaces I take, then what was the product becomes the coproduct and vice versa. So other questions? All right. So, if there's
no. So usually you write R matrix as some kind of generating function in the group, in the quantum group, right? And then it somehow is a generating function of everything in the quantum group. That's what you are.
Yes, exactly. Yeah. If you want all possible operators in your quantum group, you take all possible auxiliary spaces. You consider this R matrix. There's this R matrix, and you take all possible matrix coefficients. I mean, this R matrix will be some big operator with indices in the auxiliary space and in your spatial physical space, and also depending on spectral variables. And so that gives you, if you want to expand, if you take matrix coefficients, they expand them in whatever basis or function you would like to use, or better not to expand at all, just keep it as a function. Those are the operators of your quantum group. So there was one more question. So depends on, so the question was about Q hypergeometric functions, and so this is debatable what do you call a Q hypergeometric function, but I think this is the kind of so there's less inclusive or more inclusive definitions of a Q hypergeometric function. A Q hypergeometric function is a solution to some particular Q difference equation, and you can generalize whatever properties of that Q difference equations to more general linear Q difference equations, and call this Q hypergeometric functions. And I'm of the opinion that these are the whatever good properties the classical Q hypergeometric function has. All this have the same. Means they solve Q difference equation with just as good as the Q difference equation for Q hypergeometric function. But you may have your own definition of what this means to be Q hypergeometric, and that's according to your definition. It means a particular Q difference equation you would or would not call a Q hypergeometric equation.
Okay, so something more like Q holonomic than hypergeometric. or no?
Maybe. So this is what is true. So this is a function of a whole bunch of variables and also variable q, and at the very least it satisfies compatible q difference equation in all variables, well except the q, and then in most of the variables, in all variables except one, it's actually regular. So that's I mean it's a regular q difference equation. That's analogous to. Well, there's no more questions. Then I'll see everybody. Well, whoever chooses to join us, I'll see next week. So that would be all for today.